Welcome to Team 21013 designed a video on bacteria attenuating catheter. To start with, first we're going to introduce the background of the product.
Jackson Medical was founded because I personally believe that there is a problem in the medical device industry at the moment. I think a lot of companies in the corporate world are focused and centralized around finding ways to maximize their profits. But at the end of the day, the whole purpose of having a medical device company is to make revolutionary technology that's going to make patients' lives much better and to make good quality products. Back in 2018, I was in a motorcycle accident and it left me in the hospital for quite a while. And while I was in the hospital, I developed urinary tract infections that were associated to the catheters I was using. It was a very uncomfortable experience, really difficult to deal with, and overall it was very expensive. So that led me into looking into alternative ways to stop urinary tract infections with catheters.
A CADI is basically, it's short for a catheter-associated urinary tract infection. Basically, that means a urinary tract infection that's caused by a catheter, which usually is commonly referred to as a Foley. Just like any other time when you place a line or a tube or a drain into someone's body, you're opening the body up for the possibility of an infection. Same goes with catheters. Once you've essentially put a catheter into a urethra of a male or female, that just provides a way for bacteria and other microorganisms to get in there and cause an infection. The doctors will work with usually infectious disease or someone else to come up with the best antibiotic to treat that infection. I personally work on a ICU floor, or intensive care unit. So a lot of our patients have catheters, and depending on the patient, just like with any other drain or tube or anything else you're putting into the body, every day that's extended obviously puts them at a greater risk for acquiring an infection. So I would say my specific patient population is decently high at risk because of often the duration that they have these catheters.
75% of UTIs are caused because of a urinary catheter. 15 to 25% of hospitalized patients receive a urinary catheter during their stay at the hospital.
Over the course of a year, patients in hospitals have to pay $350 to $450 million to cover the cost of catheter-associated urinary tract infections. This is because they're not covered by Medicare, since they're not related to the patient's original problem.
The bacteria that forms CAUTI can turn into biofilm, which is hard to penetrate with antibiotics. So once the biofilm forms, it can wick up the drainage tube of the catheter or just the urethra in general to the bladder and eventually the kidneys. The current market catheters that address CAUTI are a silver and antibacterial coated catheter. 1.5 million catheters are used daily, which is a lot of plastic that goes into our ecosystem.
The male urethra is longer and more curved, so care must be taken to ensure effective and comfortable insertion for the patient. Using forceps, clean the urethra in a circular motion with cotton balls soaked in sterile saline solution. Apply 10 ml of sterile lidocaine lubricant gel from a syringe into the urethra. Using non-touch technique, insert the tip of the catheter into the urethra and advance slowly. Once the catheter is fully inserted, inflate the balloon with 10 ml of sterile water following the manufacturer's instructions. Then, very gently, pull it back until the retention balloon touches the bladder wall. Connect the catheter to the drainage bag using non-touch technique and secure it by taping to the patient's inner thigh.
First is the drainage tube. The drainage tube shall work like a regular drainage tube on a regular catheter. The only difference is that it will attenuate bacterial growth for at least a week by adding in a less than 1 milliamp current. The fixation device and the collection bag are both left untouched, so they should be used as directed by the manufacturer. The inflation port, on the other hand, has also been untouched, but for purposes of this experiment, we have used it as inspiration for a third port used for our electrodes. All changes made to this device will run through the FDA 510(k) approval process, which will be explained later on in this video.
We came up with 5 different ways to approach the medical need. The first one was a single loop, where we take an electrode through the drainage tube and then up to the balloon inflation port. We connect the battery to it, so there's an electric current running through it. The second way was a double electrode, where we have 2 different electrodes, one through the drainage tube, the other one through the balloon inflation port, both connected to the battery, but they're not connected to each other. And then the urine will act as the conductive between the 2 electrodes, causing there to be an electric current, which will attenuate the bacterial growth. The third way was the WED, which would eventually be a covering on the catheter wall. When the urine goes through it, there would be a redox reaction happening, which then causes there to be an electric current. The fourth way is the thermoplastic polyurethane, which is a flexible conductive that can be 3D printed. And then the final approach we took was a conductive polymer that we used for our experiments. After running experiments, we found out that the single loop and the WED method worked the best in attenuating the bacterial growth, but for manufacturing process, the single loop would be simpler, therefore we are going with the single loop design.
Shown here is a summary of our analysis from our preliminary round of experiments. These experiments involved looking at urine samples under a microscope and then taking images of these samples. The images were then put through image J to threshold them and then count the number of cells that were in each image. 4 images from different areas of the urine sample were taken so that we could average the cells across those images to get more realistic data. We then plotted the number of cells against which day the sample was taken from. So you see the first day is in the first column and the second day, and you see that we had a general uptick after the first day, but then our methods kicked in and the single electrode, the double electrode, and the redox reaction all performed comparable to our negative control, which was contaminated, as you see here.
The current constraints of our project is that we don't have access to a level 2 biosafety lab. We also don't have access to a class 2 biosafety cabinet. Each of those have limited us in our ability to use uropathogenic bacteria, which is transferable to humans, so we've had to use K12 bacteria, which is released to anyone. Each of our experiments will have to be redone in the future in a more sterile condition. Finally, our last concern for our project has been that we don't have the expensive lab equipment such as a fluorescent microscope in order to tell whether or not the cells that we are analyzing are dead or alive.
The U of A has allocated the amount of $4,000 as a budget for our improved urinary catheter project. Jackson Medical has allocated the amount of $15,000 as a budget. We have the amount of $14,310 in reserve. As you can see in the table or the graph, we have broken out the cost by vendor.
As Hector mentioned earlier, we'll be pursuing the 510(k) exemption process for FDA approval. This process involves proving substantial equivalence to an already existing product. Since our product is just incorporating the 4 methods that Babak talked about earlier into currently existing catheters, we believe that we'll be able to prove this substantial equivalence.
Team 21013 would like to thank our mentor, Bob Messenger, and our sponsor, Ian Jackson of Jackson Medical Solutions and College of Engineering, and of course the judges for your continuous support and attention.